Chapter 1, Moral Relations. Whether we think about it or not, engineering, or the practice of engineering, has an ethical component. So we don't often think of engineers as ethicists or as dealing with ethical dilemmas, mainly because we tend to view engineers as applying science and math and physics to real-world problems. And so it's a problem-solving endeavor that we generally attribute to engineers and not a moral problem, or at least we don't view engineers generally as faced with moral problems. What we do here in Chapter 1 is simply give an overview of how morality permeates really every aspect of engineering or an engineering problem or problem-solving in engineering, depending on how you want to frame the issue. So we're going to talk initially about moral relations and what are the moral relations that an engineer takes on when he or she becomes an engineer. So we talk role morality, and role morality really is just what it sounds like, that when we take on particular roles, there are certain moral requirements that come along with them. And usually, when we're taking on this different role, the role we take on might be, or the morality that is attached to that role might be unique to that individual. So for example, I have certain moral obligations with respect to my children that you as a student don't have. So since they're not your children, you don't have the same role morality that I do as a parent. Similarly, when you take on the role of an engineer, there are certain things that engineers are required to do, certain obligations they have, and maybe even privileges that they get that others who are not engineers don't have. So, in part, what an engineer, moral relations that define one's profession, are the same for engineers as they are for other professions. So, in engineering, you might be taught to check your calculations more than once to make sure that they're accurate. Well, this relation, that of a professional engineer, is really no different than a professional accountant or a doctor or a lawyer, that one's responsible for making sure that they are giving accurate information. Right, so this role is common to really all different kinds of professions. It's not just engineering. Where engineers become unique, or where the morality for engineers in their role as engineers becomes unique, is when we start talking about design solutions. So design solutions in that when you go to solve a particular engineering problem, this is where the truly unique nature of your morality comes in. So this is not to say that as a general professional, you don't have moral obligations to present accurate information and to be competent in your job and so forth and so on. It's just that for an engineer, where the unique notion of a role morality comes in is when we're dealing with design solutions. So it's really the intellectual core of engineering is the solution of design problems. And this intellectual core, the solution of design problems, is where we're also going to see the most substantive moral roles that you take on as an engineer. Now, when we're dealing with design solutions, there are a range of possible solutions to any particular problem. So one of the things we'll talk about initially, and we'll talk about later in the text as well, is that as we go through the process of coming up with a design solution, it's not as if any one particular design is necessarily suggested by any design problem. So consider the following example problem. Imagine that I'm concerned about safety in my neighborhood, that the street lights aren't particularly dependable, and so I'm looking for a safety light solution for the front of my house. Now, while the problem is pretty easy, the idea is that, well, I want to illuminate my front yard in the evening in some way that protects my home from someone who might have some ulterior motives in being in my yard at 1 o'clock in the morning. What are some of the possible ways in which we could approach this problem? Well, one thing we could do is simply say, well, you can put a light outside your house and turn the light on at night. Now that seems to be a very simple answer to the problem. I want to light up the front of my house, so I turn a light on. But then I might think, but that's only one possibility. Maybe I don't want the light on all day. Maybe I'm bad about turning the light on, so you might have to think, well, how can I ensure that the light will be on? So instead of having it simply a light with a switch, maybe now I want to have a photosensitive light. So when it gets dark, the light goes on. When it gets light in the morning, the light goes off. That seems to solve my problem. But now there might be another consideration, because I might think, well, really, if I'm concerned about safety, It's not about having the light on all the time. It's about having the light on when there might be somebody in my yard. So maybe now a light sensor isn't what I need, but maybe it's a motion sensor that I need. And this all doesn't take into account the fact that when I leave my light on all night, I'm burning electricity, which uses energy. So there's energy consumption questions. And the same might be true of the dimmer light, or the light that has a photo sensor. That light stays on all night, so I'm burning electricity when maybe I don't need to burn electricity. So there are a number of different approaches I might take with the safety light. And those are only a few. We can think of other things. You might say, well, maybe it's not really a safety light issue. Maybe the problem itself isn't stated properly. Maybe, in fact, what you need are sensors on your doors or windows. Maybe that's what you're really concerned about, because after all, the light may be on in the front, but what about the back of the house? What about the side of the house? What about the windows? So any design problem, when I'm talking about, I would like, if the problem's, even if the problem, I should say, is narrowly constrained, and say, well, look, I'm set on some sort of lighting solution, there's still an issue of how that solution is going to be implemented. Notice there are a number of considerations, and even those considerations are going to, as we'll see, bring in moral considerations. Now, whenever we choose a particular solution to a problem, we are making some sort of value judgment or value choice. What sorts of things do I value? For example, in the lighting situation, the value of being green conscious, right? Whether or not I'm using energy when I don't have to use it, am I being environmentally responsible with my choice of solution? You can see that if I say, well, no, I'm not, we're not simply going to go with a light and a switch, or maybe we're not going to go with a light that stays on all night and then is photoreactive to daylight or to nighttime, maybe those aren't environmentally friendly choices. And so my values come into that design, even though those designs may actually serve the purpose of solving the design problem, right? I'm looking for a way to turn this light on. Motion sensor is one, which uses a lot less energy. So maybe I say, well, design 1 with a switch, design 2 with a photo sensor. Those I'm going to push to the side and say, no, we're going to go with something along the motion sensor line. But notice that that's a value decision on my part. That has nothing to do with the engineering solution. All of those are solutions. One, though, brings in my values. And it's always appropriate to ask, could a different design produce less harm? So even if I wasn't thinking in terms of values initially, I might be thinking in terms of harm. Where does the harm come in, you might say? Well, the harm comes into environmental harms. Are those harms that I consider in my design choice? Is it human harm? Is there any other way that this harm or that this lighting solution presents a harm? Well, maybe in this case, it's very simple. That's the only one I can think of offhand. But then I might say, well, look, a light that stays on is a light bulb that burns out. When a bulb burns out, the question is, well, am I using a standard incandescent bulb or am I using a compact fluorescent? If I'm using a compact fluorescent, how will that bulb be recycled? So now leaving the light on for several hours requires that we be able to dispose of the bulb. Well, now I've got to deal with the mercury. How is the mercury going to be taken care of that's in? Even though it's a very small amount, imagine that my lighting design becomes very popular and we start selling this lighting design. So now I've got to ask myself, what happens to the bulb? Well, are we going to use LED bulbs instead of compact fluorescent bulbs? And all of these things have a impact in one form or another, whether it's mercury that could get into the groundwater, which could cause problems for individuals, could harm individuals. Maybe the production costs of LEDs are higher, which puts an economic cost onto people. So if someone wants to buy this lighting solution, we use an LED choice. That means that they might not be able to afford it, or it might be more costly, which means some people may not get the benefits of my lighting solution, which also means they may be less safe, which could also impose harm. So all of these things become moral choices. Now, all of them might not be relevant in every situation. But notice that as an engineer, I'm asking more than just, does my design solution solve the problem? I'm actually making value judgments all along the way as I'm coming up with my design choice. And this notion that designs have stages and that each of these stages has morality or a moral component to it is brought out in the text. So we can look at the stages of a design solution And we can note that at each stage of the design solution, there is some moral component we can attribute. So the statement of the problem. What is the actual problem that we're attempting to solve? And are there value judgments in the very statement of the problem? You'll notice in the book, as we'll get to in a moment, the toothpick example from the book states that when we describe what the problem is, the statement of the problem is that we want to get food out between our teeth using some sort of device. But note that even in the statement of the problem, depending on which culture you're in, the toothpick, what happens to it before it's being used or after it's being used, also becomes relevant. And so that may or may not be in the statement of the problem. So the statement of the problem itself could be incomplete. Brainstorming a solution or solutions. What sort of solutions do we come up with? Which ones do we view as viable solutions? Right? So the brainstorming part, what we actually bring into the possible solutions, and this goes right into the choosing of a particular solution, which, as we've already mentioned, when I finally do set on the sort of design I want to solve the problem, this is bringing in value judgments as well. Then, of course, there's the detail work. This is where sort of both aspects of role morality come in. The detail work on how the solution is to work and how the artifact is to be built. Now, throughout this text, we'll be talking about artifacts. An artifact just means the thing that is built. Now, an artifact could, for example, be a computer program. So it might not have a physical dimension to it. It might be electrons in a particular order in the form of a computer program. But at the end of the day, an artifact is just the thing that were built. So it's sort of a generic term for whatever it is the solution is, whether it's a car wheel or a seat belt or a lighting solution or a program. So the detail work also, which is a part of the design solution, also brings in a moral component. What are we going to build this out of? How will the building be done? Did I, as an engineer, make sure I looked at all the details of how the solution is going to work, how it's going to manifest itself in the form of an artifact that we're going to actually produce? And then, of course, the actual realizing of the design solution in an artifact. So once I've done all the detail work, the designs and the drawings and the multiple perspectives and sort of trying conceptually and in some sort of design, say a blueprint, come up with the actual design, then the question is, how is this actually going to be built? So realizing the design solution in an artifact, not just one to be built, but the actual building. And so this goes to questions of production, where it will be produced, what will it be produced out of, what sort of materials, are those materials recyclable or reusable? Are they dangerous? Are they harmful? Does the design manufacturing process present a hazard to the people who will be working in the factories designing or building this thing? I shouldn't say design, but the actual building of this thing. So again, each stage of a design solution, the statement of the problem, the brainstorming a solution or solutions, choosing a solution, the detail work, and then the final realization of the design in an artifact, all of these things have some sort of moral component to them. So as I mentioned already, the design problem, such as a toothpick example, gives us an interesting look at how a design problem is value laden all the way through. So the toothpick example, if you remember from the text, I won't go over that right now, but if you read that section of the description of what the problem is fairly complex. The problem statement does rule out some possibilities. So the statement of what the problem is says, look, there are certain things that will not be necessary to consider, but it leaves open a huge number of possibilities. So we want to make sure that we're clear that when we have a design problem and a statement of the problem, even a very detailed statement like the toothpick example, it's not the case that the design problem specifies a specific answer. It's not a deductive proof. It's not a mathematical proof. It's not a case of 2 + 2 = 4. So you could give a group of engineers a statement of the problem, and you're sure to come up with a number of solutions based on that statement. It's not a deductive sort of proof. Just like the lighting example shows that while some things are ruled out, so let's say I'm set on an illumination solution. So in my statement of the problem, it says my problem is there's not enough light in my yard. Once we rule out anything that doesn't involve a lighting solution, so sensors or a security system, that leaves open still a number of possibilities as to how I'm going to solve that problem. Just like the toothpick example shows that there are a number of different ways of approaching the problem of the toothpick. Now, sometimes we find with engineers or aspiring engineers that they don't realize the level to which creativity is part of the engineering practice. So engineering by its very nature is a creative endeavor. Right? Engineers, we tend to think of in these very technical terms, even when it comes to computer programming or electrical engineering, that these individuals are simply taking the knowledge they have, the sort of science, the application of scientific ideas, and simply applying them in a problem. It's a very mechanical, methodical sort of approach. And that may be true. There may be a number of considerations when making a design, when you're doing a design solution, that are based on what we're capable of doing and knowledge of the components that you use in your particular area or field of your engineering. But at the same time, it's really a creative exercise, as we've shown in the previous two examples. So just a toothpick example or a light bulb example or lighting example, both of these have a number of creative solutions. And so we shouldn't discount that creative endeavor in engineering. And the fact that it is a creative endeavor means that it's not wholly quantitative. It includes value judgments. And this is the sort of emphasis we want to make through the entire course, through the entire text, is that you are engaged in a value-laden activity. It's not morally neutral. There are aspects that may be morally neutral. You can look and say, this is how I calculate the resistance or the tensile strength of a material, or if you're doing dynamics or statics, you look at the forces acting on a beam and you say, this is in fact quantitative. It's fact, this is what happens when you put this kind of stress on this material. Those things are quantitative. They might be value-free, but the choice of which thing to use, which material to use, how to construct a particular beam or frame is going to be a value judgment. So you can't dismiss ethics from the practice of engineering. Now I'll talk right now just briefly about two aspects of a particular design solution. We're going to talk about the brainstorming of alternatives and the choosing of a solution. So these are just two aspects. We'll talk about other aspects as we go on in the course, but there are at least two aspects, these two, and both of these are value-laden activities, right? So the brainstorming of alternatives, which alternatives make it into your brainstorming activities, as we've already shown, is a value judgment, right? Some things you discount. So when we list, and again, we're talking here very generically about brainstorming in engineering, whatever particular field of engineering you're going into. When you simply sit down and think of it pencil to paper, pen to paper, and saying, I'm making a list of possible ways of solving this problem. Now, some of them you immediately cross off, others you keep and say, maybe we should look at this in more detail. The minute you do that, you've made a value judgment. When you finally settle, so let's say you've got 10 possible ways of solving something, and now you've narrowed it down. You said, look, this is the one. We've gone from 10, we knocked it down to 5 right off the bat, and then we looked, and of the 5 left, here's the one that we're going to pursue. We're going to choose this sort of solution. You've made a value judgment. You have not remained value neutral. It's not simply a quantitative exercise. It's not a deductive exercise. Now, we can sort of sum up in engineering, although there are a number of different moral considerations. One of the sort of primary moral principles we can apply to all engineering practice is to do no unnecessary harm. So while we'll have different sorts of moral obligations, we'll have moral obligations to individuals, to society, to employers. There'll be issues of rights, perhaps, that will come into play. Talk about a little bit of this as we talk about moral theorizing and what counts as a moral theory or a moral approach and what doesn't. The thing that we can sort of take with us as we go through the entire course is the idea that we should do no unnecessary harm. Now, why unnecessary harm? Well, in fact, there might always be a little bit of harm in anything we do. So, for example, we could say of a dentist, you should do no unnecessary harm. Well, what does that mean? It says, well, we understand that at times when we go to the dentist, there might be discomfort. There might be, in fact, pain. But that pain has a purpose. We're not harming for the sake of harming. We're not harming because it's easier if we harm. We're harming because that's the only way we can get to the desired outcome. That is to get out the cavity or to take care of the root canal. So it's unnecessary harm that we want to focus on. Now, this, of course, is a sort of slippery subject, because what constitutes an unnecessary harm? What in fact constitutes a harm? How severe does a harm have to be? These are all questions we'll look at as we go through the course. But we should keep in the back of our head right up front that, interesting turn of phrase. We should sort of keep in mind as we go through this that we're trying to minimize the amount of harm all around, whether it's to society or to individuals or to employers or to employees. Now, there are two types of ethical relations. We've already sort of talked about these. Just to emphasize these again, one, there is role morality. And so as the book talks about, role morality is our morality as a professional, as an engineer in a particular role with obligations to particular individuals. There's also morality or ethical relations in our design solutions. So our solutions themselves, when we're acting as an engineer working on a particular problem, there are then ethical relations that occur within the design solution. So let's take a look at the first of these two types of ethical relations, role morality. So as we've already mentioned, role morality is the duties of an engineer as an engineer. It's the traditional view of engineering ethics, the idea that as an engineer, I have obligations to my client, to doing my job in a particular way. Now, how can this fail, or how can I fail in my role as an engineer from this traditional view? Well, the failure points are fairly straightforward. The design problem was not well articulated. So I can fail as an engineer if I get a design problem that isn't well specified and then I make a mistake because of that lack of articulation in the design problem. Maybe it's poor brainstorming. This would be a failure on my part as an engineer. As a professional, I should do a good job. I should be conscientious about what type of solutions I've put forward. So it's possible that simply poor brainstorming. Failure to choose the best solution. Once I've gone through this process, again, this is following the sort of steps that I go through as a professional doing my job. I might fail to choose the best solution to the problem based on the brainstorming, the ideas, the things that I've excluded. Perhaps I've excluded the wrong thing. Maybe I didn't include enough in my brainstorming, which then leads me to choose something than a less than optimal solution. It might be a failure in the detail work. So as I'm coming up with my design, perhaps I lack the specificity necessary to make sure that once an artifact is produced, that it's produced in the right way. So my design lacks something. I've made a design error in the details of my design. And it's possible that the artifact doesn't realize the properly detailed solution. So it's possible in the production of the artifact. Maybe I didn't consider how the artifact was going to be produced. Or maybe the failure in the detail work just simply leads to an artifact that isn't particularly good. Now we should note that you could really generalize all of these things to any professional. So here again is why I call this the traditional view. The roles perspective failure points are really common to any professional. So you can imagine a lawyer going through a similar set of problems. The design problem was well articulated. Perhaps it was the case that the lawyer didn't think of all the possible ways in which he could approach the case. That would be part of poor brainstorming. Maybe he didn't pick the best defense. Maybe he didn't spend time in the detail work, looking at all the evidence, evaluating the opposition's case, and so forth. And then in the outcome of the trial, things weren't particularly well played in terms of how this was presented in court. So you can see that it's sort of an engineering thing, but it's also just true of any professional who just simply doesn't do his or her job properly. The second type of ethical relation comes from the perspective of design. That is the relation between an engineer and his or her design solution. And it's within this relationship between that of engineer and the solution that other types of moral failures can occur. So we have two features and two failures in a design solution. So the two features of a design problem are the conception of a solution and the execution of a solution. So we've talked about the steps in which we come up with a solution, how we conceive of our solution, and then how, in fact, that's executed in the form of some sort of artifact. And each of these features admits of a moral failure. How I think about my solution, how I conceive of a solution, and then how I actually go through and execute the solution. And this leads to probably the single most important concept in the entire course, is the idea of an error-provocative design. Now, an error-provocative design is one in which the design itself provokes error in the user or the operator. In other words, it doesn't actually matter how good the user is, how careful they are. The design itself just lends itself to errors. So the uniqueness of error-provocative designs comes from the fact that operator deficiency, that's things such as a lack of intelligence or a lack of training or a lack of motivation, don't lead to error. In other words, we can't say it's not a bad design, it's just that the person operating the artifact lacks the intelligence to use it properly. It's not the case that the design is good, but there wasn't adequate training given. So lack of training, for example, when we talk about software, oftentimes we say, look, this program is good. The problem is you just haven't used to learn it, or you haven't been trained properly on how to use it. Or a lack of motivation. We can think of a perfectly good design, but the person just doesn't care enough to be conscientious in its use. So error-provocative designs are unique in that they don't suffer from any sort of operator deficiency. They are a direct result of the individual designer creating an artifact that provokes error in the user. So at the very beginning of the textbook, at the very beginning of chapter 1, the author talks about the toaster oven, or the toaster example. So a toaster in which the natural tendency is for someone, when the toast begins to burn, to simply push up the lever that was pushed down. That is an error-provocative design. That's a design that sort of lends itself to operator error. Or I shouldn't say operator error, but causing the operator to err, even though they are intelligent, they are trained, and they are motivated. They don't want to break the device. They are intelligent individuals, and yet the non-intuitive nature of the design makes them create errors. So as we go through the text, we'll be looking at error-provocative designs, various elements of error-provocative designs. What are they? How can we tell whether something is error-provocative? How can we avoid error-provocative designs? And all of this, of course, is done within the context of morality. We have our role morality as an engineer. That's true of most professionals, or if not all professionals, the same sort of moral considerations. But as an engineer, there's a unique morality that comes from the design itself, from our relationship between ourselves and the design. And the morality then comes from the consequences of putting together bad designs. All right, so how does this become moral? Where are the values? Well, the value judgments come in the design, but also what we're concerned about is that when engineers fail to take into account how their designs can be error provocative, this leads to harm to others. So the point we made necessary is do no unnecessary harm. And oftentimes by not being aware of the fact that design itself has a moral component can lead to us doing unnecessary harms to others.